Hello, this is Mr. Henry, and welcome to lesson 4.4. Today we're talking about slope and rate of change. The essential question says, how do I find slope of the line and interpret slope as a rate of change? Okay, we've got four get the goofs here, and these four get the goofs are dealing with finding the x and y intercepts. So let's see how good we did. This first one here has an x-intercept of -1, good. Has a y-intercept of 0, no. The y-intercept would be at 1, 2, 3, 4, I'd call it at 5, that one right there. Number 2, now this one's written as points. The x-intercept is at 0, 3, so 0, 1, 2, 3, that's good. The y-intercept is at 2, 0, 1, 2, 0. That one's actually correct. Now again, you could also write this as just the x-intercept is 3. No, I lied. I lied. These numbers are backwards. This would be the point 0, 3. This would be the point 2, 0. I even tricked myself here. So the x-intercept is 3, the y-intercept is 2, but if you're writing it as points, make sure you have your points right. So the x is 3, the y is 2, like that. The third one here, the x-intercept is 0, -3, 0, -1, -2, -3. Double check myself. Yep, that one's good. The y-intercept is 2, 0. Over 2, up 0. Yep, that one is actually correct. For sure this time. Or did I do it again? Sideways 0, up and down 3. Oh, that's the y-intercept. And that's the x-intercept. See, I did it myself again. The points are correct. It's just this is the y-intercept, not the x. This is the x-intercept, not the y. Alright, vocab. We got two vocab words here. The first one, slope, is really a big topic in algebra. So the slope of a line is how slanty the line is. So you could have a slope of a line that's like really steep, or kind of steep, or flat, or going down like this. It's how slanty it is. And each angle of the line has a different slope. It has a different number. So this, for example, this line might have a slope of like 3. This line might have a slope of like 1/2. This would have like a slope of 0, and this going downhill would have a slope of like -2 or something. Okay? So each slope has a number associated, and that number tells you how slanty it is. If it's a big number, it's really steep. If it's a small number, it's kind of shallow or flat-ish. 0 is perfectly flat, and then we start going into negatives. Now the line's going facing downhill. So these are going ups, these are going down. And the way we find slope is we have this nifty little formula here. Now I have it written as like a bunch of different ways. So slope, we write the slope as this m. So m equals, now one way to think about it is the rise over the run, which is a way of thinking about when you're finding slope, if you're given a graph. So, and we'll just come up with some line here. There's my line. So from here, you're finding the change in the rise. So from one point to the other, it has a rise of that much. So from this point to that point. The rise is that. The run is that. So rise over run, I'm not a fan of that one. Change in y over change in x. I do like that one. It's the change in the y values over the change in the x values. I do like that one. Now the actual way you're going to find it, the formula, is this guy. y2 minus y1 over x2 minus x1. It is the change. This is the change in the y values. This is the change in the x values. Okay? So, the thing that I would really write down would be this. So that m equals y2 minus y1 over x2 minus x1. That is slope. That's what we're going to use probably about a bazillion times today. Now, rate of change, on the other hand, compares the change in one quantity to the change in another. Hopefully you kind of see how that relates to the slope. We're comparing the change in one thing to the change in another thing. That's what slope is. Here we're talking about x's and y's. Here's just as one quantity and another quantity. It's really the same thing, though. So, we want to find the slope of these lines. Find the slope of the line. So the first thing you need to do is you need to find 2 points where this line goes right through, I call it a crisscross, right through a perfect intersection of these little grid marks. So for example, this guy, it goes through this guy, it goes through this guy. Now I'm circling a whole bunch. You only need to pick 2. Because you just need to find the change in the y values of those 2 points and the change in the x value. So it really does not make a difference which 2 you pick. You should always find the same slope. But for the sake of this example, I'm going to pick this point here and this point here. I just kind of picked them at random. Now this point, you have to be able to find the x and y coordinate. This has an x coordinate of -1, a y coordinate of -1, -2, -3. And this point has an x coordinate 1, 2, 3, 4, 5, and a y coordinate of 0. So, we found a bunch of crisscrosses. We just picked 2 points at random, found their coordinates. Now, we're going to call this point 1, this point 2. So this is the x value, this is the y value of point 1. This is the x value, this is the y value of point 2. Now when we take our slope formula, it's going to make this job much easier. Watch. M equals y2 minus y1 over x2 minus x1. If we labeled our points x1, y1, x2, y2, now this part gets very easy. y2, which is the second y value, minus y1. And yes, by the way, you do need a minus and the -3 over x2 minus x1. Do the math on the top, do the math on the bottom. If you got a fraction for an answer, you simplify it, and we are done. So let's see, 0 minus -3 is 3. 5 minus -1 is 6. Remember KFC, keep, flip, change. So 5, keep, flip, change becomes 5 plus 1. And 0, keep, flip, change becomes plus 3. And we simplify that fraction, and we get 1/2. If you picked any other points at random, it will be the same slope, always. Now what this 1/2 says, it says the change in the y values from one point to the next, to the next, to the next. The change in the y values is 1. The change in the x values is 2. Watch. If I go from this point, change in the y value, 1. Change in the x value, 2. Change in y1, change in x2. Change in y1, change in x2. You'll notice it's going from one point to the other. This is the x value, 2. Y value, 1. So that's what this 1/2 does. It tells you to go from one point to the next. You go up 1 over 2. Up 1 over 2. Okay, letter B. Let's find some crisscrosses. This guy doesn't have nearly as many. In fact, I only see 2. I see one right there and one right there. So this point has coordinates of -1, -2, -3, -4, -5 in x, +1, 2, 3 in y. This guy has coordinates of, well, 0 in x and 2 in y. So this is my x and my y of 0.1. This is my x and my y of 0.2. So if you have this all labeled and graphed and circled and marked up like I do, it makes the rest of the problem very easy. So we have slope equals y2 minus y1 over x2 minus x1. y2 we labeled was 2, minus y1 was 3 over x2 is 0 minus x1 is negative 5. 2 minus 3 is negative 1. 0 minus negative 5, which remember if KFC keeps plus a positive 5, is 5. So we got a slope of negative 1/5. So that tells us our change in our y is down by 1. Our change in the x is over 5. So from this point to that point, I'm going to go down 1 over 5. 1, 2, 3, 4, 5. That's what the slope tells us. How to get from one point to the next. I would like you, please, to do we'll do letter C together, and then I'm going to have a few for you to do. So we're going to do letter C together. So this one's a word problem. Now, this one does not have a picture. We can still do the same thing. This is my x value, this is my y value. X value, y value. This, I'm going to call this point 1, this point 2. So I have x1, y1, x2, y2. If you do that, now you just plug them into the formula. y2 minus y1 over x2 minus x1. y2 is 4 minus y1 is 6 over x2 is negative 1 minus x1 is 3. So I'm plugging in the values from the points that we labeled. So x1 is 3. y2 is 4. Now you just do your math. 4 minus 6 is negative 2. Negative 1 minus 3 is a negative 4. And that simplifies to 1/2. So this guy has a slope of 1/2. So without even looking at the picture, I can tell you from one point to the next, you go up 1 over 2, up 1 over 2. So this guy has the line looks something like that. You go up 1 over 1 over 2, up 1 over 1 over 2. Now is where I'd like you to try a problem. Start by finding 2 points, find their coordinates, label them as x2, y2, x1, y1, all that business. Write down the formula, plug in your numbers, and do the math. See what you get. Pause the video when you're ready to go through it together. Hit play. Okay, so let's see. Find 2 points. Well, all of these are at crisscrosses, so I'm just going to pick this one here and that one there. Why not? This is the point 1, 2, 3. The x value is 4. The x value is 4. Ooh. The y value is 2. This has an x value of 4, a y value of negative 1. So we'll call this is my x, this is my y, this is my x, this is my y. Well, doesn't really matter which one you call 1 and 2. So I'll just call this one 1, 1, 2, 2. Now, we've got it all labeled and graphed and nice and pretty for us. Makes the rest of the problem so much easier. M equals y2 minus y1 over x2 minus x1. y2 is negative 1 minus y1 is 2. x2 is 4 minus x1 is 4. We do our math. We get a negative 3 over 0. You're not allowed to take something divide by 0. So, although we did our math correctly, this line does not actually have a number for a slope. The way we're going to call this slope, we say this slope is undefined. I know, I tricked you. It's undefined because it does not have a slope. It does not have a slanty. It's a perfectly straight up and down line. So when you have a perfectly straight up and down line, there is no slope. We call it undefined. So far we've seen a couple different types of slopes. We've seen a positive slope. The line's kind of going uphill. Always think about it as a little guy or a little ant walking across the line. And so ants are black. So there's my little ant. And as he's walking across this line, now this ant always walks from left to right. So as this ant's walking across the line, he's going uphill. So this is a positive slope. But if my ant hopped over to this line, now as he's walking from left to right, he always walks from left to right, now he's going downhill, which makes this a negative slope. So positive is going up, negative is going down. My little ant, well, he's kind of talented, but my little ant is not talented enough to walk on this straight up and down line. He'll just fall off. That's why this guy has no slope. This is a very slippery wall, and he just kind of falls off. So no slope. This ant cannot walk across it. It is perfectly straight up and down. Okay? We've got 2 more problems for you to try. Go ahead and do them now. E and F. Pause the video. When you're ready to continue, hit play, and we'll go through them together. Okay, so let's see how we did. Letter E, because they give us a graph, we go ahead and find some crisscrosses. There is one right there, and there's one right there. You could have also used that one, but I'm going to use these two. So this is the point. The x value is, why'd I put x? The x value is 1. The y value is -2. This point, the x value is 2. The y value is -1, -2, -3, -4, -5. This is the x, this is the y, this is the x, this is the y, 0.1, 0.1, 0.2, 0.2. Alright, m equals y2 minus y1 over x2 minus x1. y2 is -5 minus y1 is -2. x2 is 2 minus x1 is 1. Well, the bottom's easy. The top, hopefully you remember your integer rules. -5 minus a -2. Well, minus a negative turns into plus a positive. So now we have -5 plus 2. The signs are different. We're going to subtract. We're going to get a -3. So this line has a slope of -3 over 1, or we could also we could leave it like this, which is perfectly fine, or we could simplify it to -3 like that. So this line has a slope of -3. So from each point, you go down 3 over 1. Down 3 over 1. See? Down 3 over 1. That's how you get from one point to the next to the next. Letter F. It doesn't give us a graph, but it gives us points. So x1, y1, x2, y2. So m equals y2 minus y1 over x2 minus x1. y2 minus y1, x2 minus x1. Let's see, keep, flip, change. -1 plus 1 is 0. 9 minus 4 is 5. And 0 divided by 5 is 0. So in this problem, we actually got a 0 slope. A 0 slope is a perfectly flat line. I mean, if I would kind of make a quick sketch of this here, 9, -1. So go over 9, down to -1. This one, over 4, down to -1. This line, I'll draw it in black here, is a perfectly flat line. So it does not have a slanty to it. It has a slope of 0. This is different than this line, which is a perfectly straight line, but this line is going straight up and down. If we had a little, instead of having a little bug, if we had like a little man trying to walk across this line, he couldn't. He'd fall right off. A man can walk across this line. He's not going uphill. He's not going downhill. He's just walking. So this guy is walking perfectly flat, slope of 0. If this man could stand to walk on this hill right here, if he didn't fall off, he would be walking downhill with a slope of 3. Or I'm sorry, downhill with a slope of -3. Negative because he's going down. Okay? So we're able to find some slopes. What I'd like you to do very quickly is, what are the different types of slopes? Or what different types of slopes are there, and what do they look like? There are 4 different types. So I will not tell you yet. If you can, list and label and maybe make a little sketch of each of them. Take a couple seconds, pause the video, do it, and then when you're ready, hit play, and we'll go through them together. Okie dokie. So we've got 4 different types of slopes. Let me see if I can find a grid thingy here. That'll work, I guess. Let me make it a little bit smaller. There. There's 1, 2, 3, 4. Now we can talk about what these slopes look like. Okay, so we've got 4 different types of slopes. First slope would be a positive slope. A positive slope is when your line is going uphill like that. And that'd be like a +3 or a +1/2 or +4/6, something like that. They're all positive. The second type of slope is a negative. A negative slope is going downhill, like that. So this one's going up, this one's going down. And again, you can have like a -4, -1/2. Actually, I like having the negatives up top. -1/2, or a -4/8 or something. Which, these are actually the same thing. Whatever. So we got positives, we got negatives. We also have a 0 slope. A 0 slope is a perfectly flat, we'll see if I can do this. It's pretty close. Is a perfectly flat slope. That's the only thing you can have. 0. If you do your math and you get a slope of 0, that's what it looks like. Perfectly flat. 0. Not up, not down. The last one is undefined. An undefined slope is when it's perfectly straight up and down. That's close. And it does not have a number. That's what happens if you get like 4 divided by 0, because you're not allowed to divide by 0. You've heard that since like elementary school. You can't divide by 0. It's undefined. If you try to take 4 divided by 0 on your calculator, it's going to spit out some error message because you cannot do it. Okay? So it is undefined. It is straight up and down. It does not have a slanty. You cannot walk across this. All these other guys, you're walking uphill, positive. Walking downhill, negative. You're walking perfectly flat, not up or down. You're walking at 0. This guy, you cannot walk on unless you're Spider-Man, and you're not. So this guy is undefined. It does not have a slope. Okay? I'd like you to please try these couple problems out of the textbook. In each of the examples, you are finding the slope of the line passing through the points. So these come from the textbook, page 235, 236, numbers 1 through 6. Go ahead, pause the video, do them on your own. Hit play if you want to check over a problem, or if you just would like to do them together. Okay, so let's see here. Ooh, why'd you do that? Number 1. So first thing I'm going to do is I'm going to label my x2, x1 guys. So this is the first point, so x1, y1, x2, y2. I'm going to cheat. I'm going to take this, infinite cloner, and I'm going to label this one, and that one, and that one, and that one, and that one. There, I cheated, but I have them all labeled and save us some time. Okay, so now we use this formula. M equals y2 minus y1 over x2 minus x1. Since we're doing number 1, y2 minus y1 over x2 minus x1. Negative 1 minus 2 is negative 3. 4 minus 5 is negative 1. And to simplify, negative 3 over negative 1 equals 3. There's number 1. I'm going to do them all in this same space right here. So you keep working someplace else on your paper. I'm just going to keep erasing this and doing it over again. Number 2. Number 2, same formula, m equals y2 minus y1 over x2 minus x1. Here, y2 minus y1 over x2 minus x1. 6 minus 3 is 3. 4, keep, flip, change is 6. And if we simplify that guy, we get 1/2. Number 2 done. Number 3. y2 minus y1, this looks ugly, over x2 minus x1. Yes, we've got fractions inside of fractions. Let's see, the top math is easy. Negative 3 minus 5 is negative 8. On the bottom, if you remember your fraction math, you do the math on the top, you keep the denominator. So 1 minus 9 is negative 8 over 2. This guy, just this bottom part, simplifies to a negative 4. So now we have negative 8 over negative 4, which simplifies to a positive 2. See, they try to be all ugly with us and having fractions in there. It still simplified down to a nice, pretty number. That was number 3. Number 4. We've got y2 minus y1 over x2 minus x1. We get a negative 4 over 0. We are not allowed to divide by 0. This guy is undefined. It is a straight up and down slope, or straight up and down line. It has no slope. Number 5. y2 minus y1 over x2 minus x1. 0. Negative 3. This does have a slope. You can take 0 divided by negative 3. You just get a slope of 0. So this is a perfectly flat line going sideways across. And last of these, number 6. y2 minus y1 over x2 minus x1. Negative 10 up top, 5 down below. Simplify, giving us negative 2 over 1, and simplify a little bit more, if you want to negative 2. I honestly like this. When we're talking about slope and we're talking about graphing of lines and stuff, this is actually much more helpful to us than this. This tells you you're changing your y and you're changing x. You're going to see later on when we start graphing stuff using slope, we always want the slope as a fraction. So if you left it as a fraction like this, I'm perfectly fine with that. If you change it into the whole number by simplifying, I'm still okay with that. I wouldn't mark either of these wrong. I personally, when we're talking about slopes, like this better. Now, obviously, if you're talking about like fractions or adding like pieces of pizza or whatever you're doing together, you want to simplify it into this. So there was 1 through 6. Now, the second part of this is we're going to be talking about rate of change. Now, when we're talking about rates of change, we're still finding slope. So remember, rate of change is it's comparing the change of one quantity to the change of another. Well, this is the change in one, this is the change in the other. So we're still finding slope. We're just finding slope of kind of like a wordy problem. So here it says a computer cafe charges you for using the internet. The table below shows the cost. Find the change in cost with respect to time. Okay, so we're still going to be finding slope. So let's start with that. M equals y2 minus y1 over x2 minus x1. And you might be asking yourself, hey, dude, there's no x's or y's, so what do I do? Well, when you're doing this, we can find our y's and our x's. If you remember, the x variable, when you're graphing something, the x-axis is your independent. N-D-A-N-T or E-N-T, I don't know, one of the two. And the y-axis is the dependent. Ooh, that's not a D. See, unlike you, I can't turn my paper sideways. Depend, E-N-D, close enough, dependent. Well, between time and dollars, nothing can change the time. Something can change the dollars. In fact, the number of minutes you were there changes the cost. So time is independent because you can't change time. The cost is dependent because the cost you're there depends on how long you're there. So independent, dependent. And now we just pick two of these guys. And I'm going to pick this set and this set because they're small, and I like doing numbers with small things. So I'm going to call this one x1, x2, y1, y2. So I picked 2 points from my little table here. This is my x1, y1, x2, y2. If I was actually going to think about graphing this thing, I'd go over 7 minutes, up 14 minutes. Then go over 20 minutes, up 10 minutes. And that would be our graph. If I'd go even farther up, I'd go over 16, x is 16, over 16, up 32, and it'd be something like that. Okay? So y2 minus y1 over x2 minus x1. So we have our numbers. Let's plug them. Let's do the math here. We got 6 up top. We got 3 down below. We simplify that thing into 2. We could say 2 over 1 as well. So if we put our labels in here, 2 over 1, it's $2 for 1 minute. So this internet computer cafe thingy charges you $2 for every minute you're on the computer. Now let's check and see if that answer makes sense. You're there for 7 minutes. If they charge you $2 a minute, it should be double the amount of time. So double that is that. That one checks out. Double 10 is 20. Double 16 is 32. So these times all check out. They charge you $2 a minute to use their internet. That's pretty expensive. Okay. I have a very similar problem for you to try. This is example 2b. It says at Sam's Club you buy a 10-ounce can of green beans for $1.50. You could also buy a 45-ounce can of green beans for $6.75. What is the change in cost with respect to the amount of beans? Okay, go ahead and set up a little formula, a slope, find the rate of change, pause the video, and when you're ready to continue, hit play. Okay, so let's see. M equals y2 minus y1 over x2 minus x1. Now, the problem's talking about cost with respect to beans. So, cost beans. Cost with respect to beans. So now we know what our stuff is. So let me see here. I'm just going to write, because I find this, just having written out like this, a little bit confusing. So if I have 10 ounces for $1.50, and on the other side I can get 45 ounces for 6.75. Oopsie. So now I have my thing kind of written as points. It makes it a little bit easier for me. So I'm going to call this one x1, y1, x2, y2. So I have beans as my x. I have cost as my y. Okay, so y2 is 6.75 minus 1.5. That's y2 minus y1 over x2 minus x1. The math at the bottom is easier, so I'm going to do that one first. It's 35. The math up top, 675 minus $1.50. Handy dandy calculator. 675 minus 1.5, 5.25. Okay. So they're going to charge you $5.25 for every 35 ounces of beans. Now, that is a change with respect to cost, but if we can make this a little bit better, we could. If we can give a denominator of 1, which, by the way, for those of you who remember way back in the day when you were talking about proportions and stuff, back in like course 2, there's this thing called a unit rate. A unit rate has a denominator of 1. If we turn this thing into a unit rate, it's going to be much more helpful as far as our understanding of this problem. So we're going to divide top and bottom by 35. Divide 35. Divide 35. That gives us 1 ounce of beans in the bottom, and it gives us a cost up top. Let's see, so 5.25 divided by 35 equals 0.15. So now look at this. For every 1 ounce of beans, they're going to charge us 15 cents. That makes a lot more sense to me than saying, oh, every 35 ounces, they're going to charge you a $5.25. This makes much more sense as far as the problem goes, as far as understanding it goes. This is a rate. It is not wrong. This was just a little bit better. There's one problem in the textbook I'd like you to try. It says the table shows the distance a person walks for exercise. Find the rate of change in distance with respect to time. Go ahead and do that right now. Okay, hopefully you did the problem. If not, go ahead and pause the video, work a little bit longer, hit play when you're ready. But I think we're ready. So we've got m equals y2 minus y1 over x2 minus x1. Distance with respect to time. Distance, time. So my time is my x values. My distance is my y values. So I'm just going to pick 2 points. Sure, why not these two? So this is going to be x1, y1, x2, y2. Now we plug them in. We got 3 minus 1.5 over 60 minus 30. That's y2 minus y1 over x2 minus x1. I just plugged in my points. 3 minus 1.5 is 1.5, and 60 minus 30 is 30. This is a rate. It tells us that we go distance, we go 1.5 miles every 30 minutes. That is a rate of change. There's absolutely nothing wrong with that. So miles, minutes. Me personally, I'm going to change this into a unit rate. So I'm going to divide top and bottom by 30, something kind of funky though. So we get 1.5 divided by 30 equals 0.05 miles in 1 minute. So this is correct, ooey, and this is correct. I like this personally because it gives us a unit rate. It's easier to understand. This one maybe not. But every 1 minute, they go this far of a mile. Here, every 30 minutes, they go that far in miles. It's just personal preference, I believe. But they are both rates of change. Now, these last couple problems are kind of interesting problems. Let's read letter A, and then we'll describe what it's talking about. It says here, the graph shows the money made at a pizza shop on Friday night. Describe how busy the night was in words. So you're trying to put in words what's happening with this graph. Why does this graph look the way it does? So this is a pizza shop on Friday night. So you actually have to think about what goes on in a pizza shop on Friday night. Why is this line really steep? I mean, if we're talking about what this means, a steep line, it means they're making a lot of money in that time frame. This line's not as steep, which means between 5 o'clock and 7 o'clock, they only made like 50 bucks. They're not making as much money. Or between 5 and 6:30, I guess. Between 6:30 and 8 o'clock, they made about 150 bucks. So they made like 50 here, 150 there. In this time between like 4:30 and 5, they made what, 150 bucks. So why is this steep and then shallow and then steep? Just think about a real life situation. Well, the way that I would kind of rationalize this is, I mean, this is people getting home from work. They don't want to cook dinner. It's Friday night. Heck, let's go get some pizza. So they're making a lot of money. This is like the dinner rush. So this is dinner. Oh, can I turn this thing sideways? Let's see. Ooh, I can't understand that thing. So dinner. So this is the dinner rush. People going for dinner. They don't want to cook. Okay. And it slows down because after 5 to 6:30, people have had their dinner. So this is kind of like the after dinner or late dinner people. There's not many of them. And then from 6:30 to 8 o'clock, we have this jump again. Why would we think that? Well, it's Friday night. What happens Friday nights? You know, you get your groove on, get hungry. Well, get some pizza to fill that groove. So we get this extra little boost here because people are buying more food, they're having parties, they're getting get-togethers. So we have our festivities, we'll call it. Our festivities, our parties, our get-togethers. That's all happening starting at like 6:30 or later in the evening, so we get a little more boost in the amount of money we made. So just by looking at this picture, we can kind of figure out what's going on at this pizza shop. They get a lot of money for dinner, and then people kind of straggle in for this late dinner area. And then we get a bunch more money during the evening because people are starting to have get-togethers and people are off of work and they've changed their clothes and they're having parties and all that kind of stuff. Letter B. Letter B here says, a student commutes from home to school by walking and riding a bus. Describe the student's commute in words. Alright, so we've got minutes and miles. And if you don't understand what this is showing his speed. I mean, if you go 1 to 3 minutes in 1 mile, or this doesn't always have to be 1 mile in 1 minute, but if he goes 3 minutes and it goes that distance, and he goes 3 more minutes in that distance, and then he goes 2 minutes in that distance, he went a lot farther here than he did here. Okay, so what is this graph showing? Well, let's see, this guy, student walks to school, so he walks and he rides a bus. Oh, okay, so let's see. Well, he's not moving very fast, so this is probably when the kid's walking. And now he's just kind of standing still. Like his minutes are increasing, but his distance is not getting any farther. So why would the dude just stand there? Well, I guess maybe if he has to wait for the bus, he would stand there and wait for the bus. And now he's going really fast. Well, the really fast thing, he's probably not like, well, unless he missed the bus and he's running to chase after the bus, but he's probably actually riding the bus here. So the bus is moving fast, much faster than he could walk. So he walks a little bit. He doesn't have a lot of speed. He waits for the bus for a little bit, and now he's riding the bus, and his speed is much quicker. Okay? Go ahead and try this letter C on your own. See what you can make of this. And then we'll get back together here before too long. Okay? So the graph shows a ferry's trip across a lake. Describe a word. So the ferry is like the big boat that people get on, and they go to, like, I don't know, they go see some scenery or whales or something, or they want to go across a channel, and sometimes they're big enough you can put cars and stuff on them and that kind of stuff. So graph shows a ferry's trip across a lake. Describe it in words. So we got this minutes and distance thing. So again, the slope of this is showing the speed. So right now the speed is 0. It's not moving at all. So why would the boat not be moving? Well, if people are getting on the boat, so we're loading people. So we're sitting on the boat, we're loading people up. Okay. Now the boat's, it's not going super fast, but it's going kind of fast. And then it picks up speed. So why would the boat be going slower here and then faster there? Well, if you've ever been on a boat before, in that little area, so if this is like the land, and the boats are coming out here, the boats have to slow down until they get out in the open water. So maybe it's just going slow, or it's kind of picking up speed. So we can call this moving slow, or like getting out into the open water or something like that. Now, look at this. Look how fast this thing's booking. It's going pretty quick. So it's out here in the open water now, and it can just take off as fast as it wants. So I'll call it booking it. This little boat's booking it. It's getting to the other side of the lake as quick as it can. And now look at this. The distance, this time thing, its speed is 0 again. Why would the speed be 0? Well, what if it got to the other side of the lake? The people aren't going to jump off while it's moving, so it has to stop over here for people to get off. So, loading, unloading. So the boat's loading over here. Then it goes kind of slow as it's going across this little narrow spot. And then it's out in the open water, and it books it really quick. And it stops on their side for people to get off. Go ahead and try this. This one's out of the textbook. It says, using the graph in example 7, which I've included for you. It says, draw a graph that represents the student's commutes from school to home. So this was the commute from home to school. It wants you to do the opposite. It wants a commute from school to home. Okay, so let's see. So it looks like here, this is kind of similar to the problem that we did. The kid kind of walks to school, or walks to the bus, waits for the bus, and then rides the bus. Okay? Now, we want the opposite. So think about this. The way back, the kid's going to ride the bus home. So his distance from his time and distance thingy, he's moving very fast at the beginning. So he's riding the bus to the bus stop. So his speed is going to be quite high. So there's his speed. So he was riding the bus. Now, he's at the bus stop. Is he going to wait at this bus stop for a while before he starts walking home? Probably not. That wouldn't make much sense to me. Then I'd say once he gets off the bus, he's just going to start walking home. So he's just going to have this little slower increase as he's walking home. That looks a little better. Take your time and everything's much prettier. So he goes really fast on the bus, and now he's kind of walking home at this slow speed. He doesn't need to wait for the bus. He's getting off the bus. He's not going to wait at the bus stop for a while. Okay, summary. So what does the shallowness or the steepness of a line show? So we saw some really steep lines. We saw some really shallow lines. Those are the ones that kind of like more flat. That's kind of shallow and that's kind of steep. What's that show you? See if you can come up with a sentence or two, a description. Think about it, write it down, and hit play when you're ready to continue. Okay, so the steepness or the shallowness of a line, it really shows this rate of change. Now, in some of the earlier problems we're doing, this rate of change was just talking about on a coordinate grid, from one point to the next, from one point to the next. That's this rate of change. But when we're talking about these word problems, the rate of change actually had a meaning behind it. Here, the steepness or the shallowness showed the speed this guy was walking to school. Here, it was showing how much money they made. So the steeper line, they made a bunch of money. The shallower line, they didn't make as much money in that time. So the steepness of the line can actually show some information. So it's not moving, it's moving slow, moving fast, not moving again. That tells us something about what this boat's doing. So it's this rate of change. And the homework we have here comes from page 239 through 241, numbers 2 through 22 even, 38 and 39. So more than likely there's going to be a bunch of problems where you are finding the slope using m equals y2 minus y1 over x2 minus x1. And these two are probably little wordy problems like we were just doing here a second ago. All right. Thank you for watching lesson 4.4. Bye-bye.